Hi everyone, and welcome to another Teva API webinar. My name is Tammy Ben David, and I'm your host for today. Thank you for joining us wherever you are in the world. We're really happy to have you here. So today we're going to be talking about the topic sustainability by design, implementing safe solutions to reduce risks. So just to give a short intro about the topic, environmental health and safety considerations, or what we call EHS, are crucial to the API product lifecycle. Here at Teva API, we have a team that's dedicated to ensuring safe solutions are implemented from the earliest stages of API development all the way through to the commercial stage. They've carefully crafted process sustainability as part of product lifecycle management. So the webinar today will be about 40 minutes long. In the first 30 to 35 minutes, you'll learn about the following topics: what sustainability in the labs actually means, how to identify highly hazardous materials, why flow chemistry is a hot new technology, how to judge if a product is safe or needs to be let go, and what equipment is needed to discover risky situations. After this, I'll open up the floor for questions. So please, if at any time while our speakers are presenting, you have a question to ask them, pop it into the question box on the side of your screen where you see the two little speech bubbles, and then we'll try to get to as many as we can at the end. So now I'd like to introduce our speakers. We have top EHS experts from Teva API with us today. First of all, we have Franjo Jovic, who is the principal pilot engineer at the Pliva site in Croatia. He is the global subject matter expert for process safety and a computational tool expert. We also have Gash Bartal, who is the director of sustainable operations and green technologies in Teva's global manufacturing tech support group. His fields of interest include sustainability, circular economy, and waste treatment. And last but certainly not least, we have Moshe Tergiman, Associate Director of Process Safety at Teva API. His fields of interest include safe handling of hazardous materials and chemical reactions, fire and explosion prevention, risk assessment, and safety audits. So I think we're ready to start. Over to you, Franjo.
Thank you. Hello. So I will speak about the safety aspects of process development. The main question we have to ask ourselves during the research and development of our processes, are the processes we develop actually safe or not? So this is the key component of process development. And moreover, what is the amount of information we need to provide to our colleagues in production, in EHS, in engineering, in order to keep these processes safe in our production vessels and equipment. If you still ask yourself, do we actually need a safety assessment of our process? These are one of few of accidents we had in May of 2022 in the news, Croatian news, in surrounding countries like Slovenia and Bosnia. So you can see here quite dangerous and quite, let's say, serious accidents, which also had a fatal consequences in life lost. So yeah, it is important to emphasize that it is really important to never be see on topic on our news, like, or in our countries, the name of our company in it. So yeah, that's why important is to have this aspect. In Teva, we built a safety lab in which we have certain equipment. We call this calorimetries, and from my perspective, it is really sufficient amount of information to, let's say, understand the process and to have go or no go decision. One of really unsafe process we had in our past. This is the example of process in which we used dimethyl sulfoxide as a solvent. Dimethyl sulfoxide is a common solvent, highly aprotic, high boiling point solvent. And you can see here on the up left the curve in which we had heating to higher temperatures reaction samples. Once when we reach certain temperature, we triggered this decomposition reaction, and you can see sudden increase of temperature in which we had more than 10,000 degrees per minute heat generation. And also, moreover, what is particularly dangerous, it's also pressure rise with this process. And of course, we try to understand that, to dig a little bit in scientific papers, and we find and discover there is a well-documented case of degradation of dimethyl sulfoxide. Of course, we put this process back to research and try to, let's say, avoid usage of dimethyl sulfoxide with something much safer. One thing is to have, let's say, measurement and crew data. The additional, let's say, step is to analyze and to put all this data we have into some kind of analysis. So that's why we put all these temperatures, what we call here critical temperatures. And the regular way of doing our processes is to charge material in reactor, heat up to the temperature of process, and more or less all of our processes are exothermic, which means they deliver heat to surrounding. And if we have certain case of what we call cooling failure scenario, which means simply we cannot cool because rate of cooling is much lower than rate of heat generation, then in that case temperature could be increased, and this could trigger secondary reactions. There is a reason why we call this runaway scenario, because once when you have this, let's say, example, the only way you can do is basically to run away from your plant in order to save life. So it is really important to have this temperature of the decomposition much lower, much higher than the maximum temperature which could be, let's say, observed in our equipment. So, okay, we have information, we have analysis. Moreover, we could use all this data in different kind of analysis. What is particularly interesting, we could use this data in computational tools to understand process, different kind of possible scenarios, see the consequence of these scenarios. And again, with calorimetric measurement, we can additionally do the safety analysis. And this effort is called safety by design. We tried to do that also during 2015. This was a little bit my, let's say, additional task, because I really wanted to be sure to double check myself. During 2015, we had certain risky process. And I wanted to publish this paper in, let's say, international community. And basically, we use simulation tools. We use this safety by design methodology. And we put all this together and publish paper in order to share our knowledge with our, let's say, not only scientific community, also with our competitors. So from this point, basically, we are able to do much more than we are currently, let's say, delivering to our colleagues in production. Why is that so important? It is important to have this information, and the really perfect example to explaining that is the Beirut explosion. It is well known that ammonium nitrate is it is considered as explosive. You can see here on this also in scientific paper, there is a sharp peak of decomposition of ammonium nitrate. The lucky or good thing is that this temperature is quite high. It's something around 400 degrees. And they had like this pretty bad scenario in which they had fire, which led to increase much higher temperature than usual, and they basically trigger this secondary reaction. The consequence
rocking
of that,
the capital of Lebanon. Look,
you can see here on this
wow. All right,
video.
we have
it is
a live
devastating.
look now
you can see
at this
and
apocalyptic
pretty
scene
sure
in the city of.
I believe that you all know the news from these days in which this scenario happened. You know, massive destruction, tons of materials went into explosion, and sadly a lot of casualties, a lot of material demolition, etc., etc. And I'm always remembering this video of this bride, which during the let's say, for a young female, it's really important day, and basically in that moment, it's actually moment when this explosion happened. In our facilities, we have active pharmaceutical ingredient, which also quite energetic, and in certain conditions, they also can go into this not only degradation, also decomposition. That's why we also perform the test of all of our materials with this test, what is called minimal ignition energy. This is the amount of energy which is required to ignite combustible dust. And I have one of examples during my process development. I have a case in which you can see here the AP power is dispersed, the ignition is basically started, and you can see the blast of on small scale. So also on scale up, we have our production with much higher scale, hundreds of kilo. So that's from this point, basically, we also covering these scenarios. So these, let's say, standard operating procedures we use in research and development in order to cover all these risky scenarios. And particularly, it is important to have this what we call intrinsic safety in case of these unwanted scenarios, that we still have like internal safety boundaries which could not lead to these scenarios what I just tried to explain with these examples. So yeah, this is my part. So back to my colleagues.
Franjo. And hello everyone. In my part, I will discuss what is process sustainability, why do we need it, and how we in Teva API embedded it into our process, like a product life cycle. So the basic definition, or the most common used definition of sustainability, is meeting the needs of the present without compromising the ability of future generations to meet their own needs. Now, when we are talking about sustainability, we mostly refer to the environmental aspect. But in fact, sustainability is a combination of the economy aspect, environment aspect, and also social. In order to be in sustainable position, we need to balance between all those three elements. From the production point of view, sustainability means the ability to maintain or support a process continuously and over time. When speaking about pharmaceutical industry, it's well known that our industry is resource intensive. Analyzing the life cycle analysis assessment of production of drugs, we identify the API part as the biggest contributor to the sustainability of the pharmaceutical industry. Benchmark data identify that we are producing 150 kilogram of waste per 1 kilogram of API we are producing. We are using solvents up to 90% of our mass in API production coming from solvent and water. 80% of the environmental footprint of API production is related to solvent and energy management. It is clear that if you want to improve your performance and reduce your footprint, you should focus on the API production. When looking on API life production or product life cycle, we can identify three main steps. The first one is the development of a new product. The second one is launch to market. And the third one is commercial production. We in Teva identified two main barriers when we are considering incorporating sustainability into our process lifecycle management. The first one is that the impact of sustainability is increased related to the production volume. When your volumes are low, the impact is low. When your volume increased, the impact is increased. Now, this is very tempting to delay the incorporation of sustainability into the process lifecycle management. But at the same time, the second barrier is that as we go along with the process, our ability or flexibility to implement changes into the process, it's becoming much more complicated. This is why we adopted the concept of sustainability by design. And the idea is that we are trying to develop our processes to be sustainable in advance. And we see that our biggest impact could be achieved during the development stages. But it not means that we are stopped there. The world is dynamic and changing, and it means that we need to evaluate the sustainability along the way and make sure that our products remain sustainable also when it comes to be commercial. Now, as I said already, process sustainability is a question of balance. Find the right balance between different aspects. Like in music, if you manage to balance between the different elements, you will be able to achieve harmony. The same for process sustainability. When we are developing our processes, we need to consider and balance between different elements. Each element contains many parameters. Now, you can see some of them like safety, environmental aspects, legal, control, economy, and also throughput. Now, the sustainable process should offer the best balance between the different elements and parameters. But again, as I said, the optimal position is for this day and for the near future. We have to continue reviewing the situation and make sure we maintain process balance and sustainable also in the future in different time stage. Now, for few examples how we are doing it actually in our process development. So everybody knows that if you want to promote sustainability, you need the green chemistry or the sustainable chemistry is a very good way to do that. We have the 12th principle of green chemistry that each one of them gives us the benefits both of environmental and also economical. And this time I want to focus on principle number 9, catalysts. It is clear that if you use catalyst, you have better, more sustainable reaction, less waste, less material consumption. And this is something that we are highly desired. Some chemical reaction need the use of catalyst is must to use in order to perform. Now, most of the catalysts are metals, and even more than precious metal. And as you can see on the right, some of the metals are, for example, are palladium. And as you can see, the demand for palladium is increasing, and the future is uncertain. The price of palladium is increased in the last few years dramatically. So what we are doing, If we keep on going like business as usual, it is clear that we will not be in a sustainable place. So in order to balance and regain the sustainability, we need to take action, like considering recovery or recycle the catalyst back. So this is very common for heterogeneous catalysts, and we are doing it for years. But for homogeneous catalysts, this is something that is new. So if we want to maintain or improve the sustainability of chemical reaction using homogeneous catalyst, we need to incorporate the recovery of the catalyst well in advance, even during the development of the process in R&D. Other options that we develop internal tools that help us to classify and evaluate the inherent risk of solvents and reagents. As you can see, using this tool, we are able to identify EHS hotspot and the risk of using specific chemical, and of course try to avoid it. And if not, and if we can do that, we can mitigate it and be sure that our process is safe. You can see on the list on the left, for example, comparison between different kind of amide formation reagent. You can see out of the list that COMU reagent is classified as problematic, and it looks like for this specific or this comparison is the most attractive or most sustainable chemical to be used. And as you can see below, from the Sigma Aldrich site, this was highlighted as a green solution for amide formation. So there is a good correlation between the analysis that we made using our tool to what the supplier is also saying to us. The same, for example, for reductive amination reagent. We have, for example, STAB as one reagent that we are using, and the second is the sodium borohydride. As you can see, STAB is classified as a problematic, whereas sodium borohydride classified as hazardous. Again, if possible, it will be better to use STAB, which will end up with a more stable and more safer process rather than using sodium borohydride. The same was also highlighted in the pharmaceutical roundtable green chemistry site, that's saying that STAB is a mild reductive agent. So having said that, I will thank you and move over to Moshe Turjaman.
Thank you, Gash. I'll take it from here. So now that we have assessed our processes and we know what is the criticality of the route of synthesis as explained by Franio based on experimental data, and how to ensure that our process is sustainable, we can move to the next stage of implementation of solutions, how to reduce our risk. So what do we do in Teva for this risk reduction? Of course, we start with safe material selection, as described before by Gash. We look for better waste treatment, the composition of the waste and how to treat it. And we look for safe work processes. Let's see how we do it. We start with responsible and inherent safety reviews. We developed in Teva standards and guidelines which describe the elements of responsible and inherent safety reviews. Then we go through the green chemistry principles described in our guidelines and design principles which is more through the engineering design. So what is a responsible and inherent safety design? It will ensure that our process is optimized, sustainable, and will get the best procedure to go through a product development. So this is our guidelines. They were all distributed in all Teva facilities, trained by the EHS, engineering, and operational operators. So let's go through the process and the elements of responsible inherency safe design concept. Starting from left to right, these elements that we implement, starting with elimination of hazard. If it's possible to eliminate the hazard to start with, that's the first choice. The second way to reduce the risk is to minimize the hazard. We will get into this in the next slide, an example how we can minimize the hazard. The third option is to substitute the hazard. In industry, it was done already before. For example, in the paint industry, we used to have paints that are based on solvents, flammable solvents, which were replaced by water-based solvents, latex type paints. So we took similar approach in our equipment cleaning. Instead of using flammable solvents, in most of our cases, we use water-based detergents. So that's a substitution of hazardous material with less hazardous material. The fourth a potential reduction of risk is moderating the hazard. We'll look, for example, we can reduce the pressure, we can reduce the temperature whenever it's possible, and we go through this step during our R&D stage. And last is simplifying. Many times complex way of synthesis and complex operations can generate hazards, and simple process is always a better solution to reduce the risk. So for example, one of the ways to minimize the hazard is to go through to use process intensification, and we adopted in Teva the possibility of using chemical reaction or going through chemical reaction with flow chemistry. Flow chemistry is in the market for a decade, developed slowly by the pharmaceutical industry, adopted actually by the pharmaceutical industry. And let's see what are the elements and benefits of flow chemistry. Starting from left to right, this technology will allow us to have better reproducibility and robustness. It is flexible. It takes a relatively small space comparing to large unit of reactions and separation units. It will allow us to go through extreme reaction conditions. Sometimes you need high temperatures or high pressure, and also very highly toxic materials. So this technology, since it's using relatively small equipment and it's a flow chemistry, it will reduce the risk. The next step, it provides a better, superior heat and mass transfer. It is fully automated, good control for the process, and finally, it will support us in doing scale up. Moving from lab scale to production scale is done in an easy way and a successful way. We can see here in these photos examples of our different type of sections of the production. It's We have on the left chemical reactors, we have at the bottom continuous extractions, and so on. All these skid units, they look small, but the capability to produce industrial quantities are in place. Let's look at another example how we can moderate or substitute a hazardous material. We had one situation when at the beginning of at the early stage of R&D development, the chemist, the researcher, found that phosphooxychloride would be a good reagent to be used at 110 degrees, which will provide a good product, high quality product. Once we analyze the usage of this material, phosphooxychloride is known as a water reactive material, will react violently with water. We checked for possibility to substitute it with, although with another water reactive material, but which is much milder. And if we look at the bottom, when we do the comparison with the GHS phrases for both materials, the material on is for another example for lead nitrate that was also considered for another process. In our analysis, we managed to replace one highly hazardous reagent with a less hazardous reagent. So once the Brutus synthesis is completed and we all agree upon it, and we do it through a few phases of assessment. We have a phase one when we assign the route of synthesis, then the second phase when we look through the criticality data, and then the process will move to the next step of piloting. We go through design principles, which is more related to the engineering and design aspect, and we with the preferred way to go through the design engineering is starting, of course, with the responsible and inherent design. We implement another three ways, principles how to reduce the risk. The first one is to implement passive design. Passive design, for example, is something that you do without the intervention of an operator. It's always there. For example, when you place a firewall that will prevent fire to go from one place to another, this is a passive design. Or when you store flammable material or toxic material in a dike, or what we call a second containment, that's an example of passive design. Then additional to passive design is active design. Active design is the engineering design when you implement instrumentation through control, interlocks. For example, if we want to avoid overfill of a tank, so we implement instrumentation, level switches, and interlocking the flow to the tank. And last way of controlling the risk is by procedures. Whenever there is a potential high risk, we provide detailed procedure, step by step, how to go through the operation. So if we go and we have all this data, and we just about finishing the pilot, the small quantities manufacturing. Before we go to the full production, we prepare our basis of safety. Basis of safety, in a way, it's a methodology, or it's a it's a document that is prepared, and it includes all the elements that were described from R&D through the sustainability process. We prepare procedures that are based on this data. We look for deviation through risk assessment. Normally, we go through hazard and operability risk assessment. We and we assign the acceptable risk through our principles. Whenever the risk is not acceptable, we look for engineering ways how to reduce the risk. We understand the material properties. We go through each material with a thorough analysis of its properties and what is the most safe way to handle the material. Then we select the equipment that will stand the corrosion, the pressure and temperature that is required for the process. And last but not least is the human factor. We always take in account that we have an operator that need to go through this process, operate it in a safe way. Thank you by now, and please, if you have questions, we'll be glad to respond.
Thanks so much to all of you, to all our speakers, Franjo, Moshe, and Gash. While you were speaking, we received quite a number of questions from our listeners. So we don't have time to answer all of them, as I mentioned before, but we'll touch on a few at least. And whichever speaker feels most suited to answering them, please do. So the first question is, do you have a system to evaluate product sustainability?
Yes, I will take that. Me, Gash. Yes, we have a tool, internal tool that we developed. We called it eco-efficiency. And we call it eco-efficiency because it, of course, a combination of both ecology and economical evaluation of the product profile. In this evaluation, we score different aspects of the process, like temperature, solvent selection, yield, volume, and other aspects. Each aspect gets a score, and the entire product gets an aggregated score that can reach up to 100. So if the process is sustainable, you get the maximum score, and as your process is less sustainable, you get lower score. Now, but once you have the score, you can analyze and you can act upon the score and know where your, let's say, place to be improved later on in the product, in the life cycle management, and even take actual online action in advance.
Thank you, Gash. Okay, next question. Is there a system that helps to exclude an unsafe process? Are all processes in Teva API safe?
Yeah, I believe this is the question for me. So I will try to answer this question. What is really important when we all discuss about different aspects of process development, well, emphasis is on understanding. So you put all this knowledge, together, and you have to deliver this amount of information to production. But we have the system we adopted in Teva from scientist Francis Stessel in late 2000, in which we put all of our processes into criticality class, which means ratio of different temperatures will tell us which kind of criticality class we have. Criticality class 1 means safe process. We can go further up to criticality class 5, which means unsafe process, and we need to rework it. So from this kind of approach, we have this in our guideline. We put all of our processes, and from this approach, we can distinguish what is safe, what is acceptable for us, and what is not. So I hope I answered this question.
Thank you. Thanks, Franyo. I think we have time for one more question. So the question is, could you provide, please, an example of implementation of inherent safety in design with a passive element? Moshe, let's hope this one's for you.
I think this is for me. Yeah, I'll take it. Okay. Yeah, of course. Once we, as Franyo mentioned, that we got the criticality of a reaction, and our internal way of analyzing for high risk reactions, criticality 4 and 5, we go through designing of emergency relief system. Now, to design a proper emergency relief system, you need the data that we develop at the early stage of development, and we use also external world acceptable software called dyers. In this software, we plug all the elements of the chemical reactor, the volume, the size, the quantity, and then by getting the data of the reaction, heat of reaction, and the possibility of gas release, we design the proper vent sizing in case of emergency, in case of runaway, as Franyo described at the beginning. So this way we implement our development data to and implement it in engineering passive, we would say passive instrument like a relief valve or a rupture disc.
Okay, thank you very much. So that's all we have time for today. If we didn't get to your question, don't worry. Our experts will be answering all the ones we didn't get to in the next few days, and we'll be sending the answers to your email. If you'd like any more information about our products or services here at Teva API, please feel free to reach out to us by email. And for more great content like blogs, podcasts, and previous webinars, please check out the website teva-api.com. Thanks for joining us. See you again next time. Bye.